Hello, Arduino Piano Part 2 will handle the audio amplifier output stage. I will discuss with you several audio amplifier classes, and two of them I will build up and do measurements. See you after the intro. In today's video I will discuss with you several audio amplifier classes and then calculate and measure a real class B amplifier and calculate and measure a real class AB amplifier. And at the end we will do a sound comparison of a class B and class AB amplifier. For audio amplifier, following classes needs to be considered: class A, class B, class AB, class G, class H and class D. How the basic circuits look like and what are the pros and cons of each class I will discuss with you now. One remark before we start. In the basic circuits I have omitted all parts which are necessary to handle part tolerances and temperature dependencies. When we calculate later a real circuit, we will introduce such parts. The basic principle of a class A amplifier is easy. With zero input signal, we trim the current through the transistor in such a way that this point is at 0 volt. When we then apply a small input signal to the base, it will result in a bigger voltage signal on the collector and we will hear it in the loudspeaker. The advantages of a class A amplifier are low distortions, simple construction and high voltage gain. The disadvantage of the class A amplifier is the high quiescent current. If we have no input signal through the resistor R3 and the transistor, half of the maximum current is flowing. This means that at high power output stages a lot of heat is dissipated in R3 and in the transistor even with no input signal. Class A amplifiers are used usually in preamplifiers where we need a high voltage gain and have usually low currents, that the quiescent current problem is not an issue. The class B amplifier solves the problem with the quiescent current. If we have zero input voltage, the voltage drop of the Base-Emitter diode is zero and so there is no current flow through this transistor. Also on the negative side, the Base-Emitter voltage is zero and therefore we have no current through this transistor, and in the end we have no current between plus supply voltage and minus supply voltage. If we increase the voltage at the voltage level of 0.7 volt, this transistor will open and current will flow through the loudspeaker. Due to the fact that this emitter is always 0.7 volt below the base, the loudspeaker will follow with a difference of 0.7 volts the input signal. And the same on the low side. If the voltage decreases below minus 0.7 volts, this transistor will open and current will flow, and the emitter of this transistor will also follow the base and the input signal with a difference of 0.7 volt. If we apply a sine wave input signal from 0 to 0.7 volt input signal, the output will remain at 0 volt, and above 0.7 volt it will follow the input signal, and below 0.7 volt it will be again 0 volt until it is below minus 0.7 volt and follows the input signal, and if it is above minus 0.7 volt we will have again 0 output signal, and these plateaus are responsible for large distortions. So we can summarize: no quiescent current, simple construction and high current gain. Cons: voltage gain below 1 and large distortions. And that is the reason why this type of amplifier is usually not used at audio amplifiers. The class AB amplifier solves the problem with the 0.7 volt gap. If we connect the supply voltage via a resistor and a diode to the input signal, then this point is always 0.7 volt above the input signal. And if we then lose here 0.7 volt, this voltage level is the same as the input voltage level but with a higher current. At the negative side, this point is always 0.7 volt below the input signal, and with this 0.7 voltage drop we have here also the same level as the input signal, and again with higher current. The temperature effect on the base-emitter diode could result in a big cross current through these two transistors. To limit the cross current, there are additional resistors here and here necessary, and that is the reason why the voltage gain even on this circuit is in reality below 1. Class G amplifiers are often used at high power amplifiers. For high power amplifiers we need a high supply voltage to drive enough current through the loudspeaker. But with a low input signal on the high power amplifier we have a big voltage drop on the output transistor, and a big voltage drop multiplied with the current gives a lot of power which is dissipated in the transistor. This makes this amplifier inefficient, and to improve the efficiency of the power amplifier there is a trick that with low signals we use a lower supply voltage, and at high signals we use a higher supply voltage. In the middle of the circuit we can see a usual class AB amplifier which is supplied via these two diodes from the positive and negative a lower supply voltage. When the input signal rises above a certain threshold, the higher supply voltage is switched to the output transistor. From here to here we have this voltage drop which causes power dissipation, and from here to here we have this voltage drop which causes power dissipation. So in the end this amplifier has a better efficiency than the normal AB amplifier. Also this amplifier has a little backdraw on this point. When the supply voltage is switching and the output transistor is not changing fast enough his conductivity, then we have here a little bit distortion. The class H amplifier solves the problem by smoothly increasing the supply voltage. So the output transistor need not to quickly change its conductivity at this point. In the middle we have a normal AB amplifier circuit which is supplied via these two diodes from the lower positive and negative supply voltage. This emitter is connected to the Zener diode, and now let us assume the Zener diode is for example 5.4 volt. Then this point is 5.4 volt above the emitter, and then we have here the voltage drop of 2 times 0.7 volt. So this emitter is 4 volt above this emitter. With low input signals this collector is clamped to UB1 minus 0.7 volt, the voltage drop of this diode. When the input signal rises above UB1 minus 4.7 volt, this transistor is taking over the supply of the output transistor. And due to the fact that the output transistor need not to change its conductivity quickly at this point, we have lower distortions than a class G amplifier. When high efficiency is required, class D amplifier are the best choice. Efficiency of 90% and more are possible. At class D amplifiers, the output transistors are either completely conductive or completely isolating. If they are isolating, they have a high voltage drop but no current, so we have no power loss. If they are conducting, then we have a high current but a very small voltage drop, and we have a low power loss. Only at the switching point we have a high current and a high voltage at the transistor. but this switching time is very short, and in the end, in the middle, the power loss due to the switching is very low. To get the variable output voltage, the PWM modulation is used. At 0 volt output, the positive supply voltage and the negative supply voltage are turned on each 50%. For very high output voltages, the positive supply voltage is turned on for a very long time and the negative output voltage is turned on only for a very short time. For very low output voltages, the negative supply voltage is turned on for a long time and the positive supply voltage is turned on only for a short time. With a low-pass filter, the high-frequency PWM is filtered out and it remains a low-frequency analog voltage. One possibility to generate the PWM signal is a very fast triangle oscillator, and its frequency should be much higher than the maximum audio frequency. When the input voltage is below the triangle, the lower output transistor is turned on. When the input voltage is above the triangle, the higher output transistor is turned on. With 0 volt input voltage, the low side transistor and the high side transistor are turned on each for 50%. At a very high input voltage, the low side transistor is turned on for a short time and the high side transistor is turned on for a long time. At low input voltages, the low side transistor is turned on for a long time and the high side transistor only for a short time. Another important point is to ensure that both transistors are never turned on at the same time. To ensure this, these two diodes shift the threshold for switching the two transistors in such a way that always one transistor is turned off first and then the other transistor is turned on. So we have an amplifier with a very high efficiency, but on the con side we need inductors and we need an increased effort for EMC shielding. Before we start with the calculation of the real amplifiers, we will summarize some important boundary conditions and datasheet information. The supply voltage should be like Arduino 5 volt or 2 times 2.5 volt. The temperature range should be 0 to 40 degrees Celsius. The input voltage should be within the supply voltage from 0 to UB. The output voltage should be within the supply voltage from 0 to UB, or if we decouple it with a capacitor from minus UB half to plus UB half. And from the speaker datasheet we know the impedance is 16 ohm. We will use the NPN transistor BC547C and the PNP transistor BC557C. Both have the similar data. The maximum power dissipation is 500 milliwatt. The current gain is 150 at 100 milliamp. The maximum continuous current is at the NPN transistor plus 100 milliamp and at the PNP transistor minus 100 milliamp. And the maximum peak current is at the NPN transistor plus 200 milliamp and at the PNP transistor minus 200 milliamp. The maximum junction temperature is 150 degrees Celsius and the thermal resistance of the housing is 200 degrees Celsius per watt. Now to the real amplifiers. The Class B amplifier is the only one where the principal circuit and the real circuit are identical. The maximum current we will get when the input is at the positive supply line. So we have 2.5 volt minus 0.7 volt from the Base-Emitter diode divided by the loudspeaker 16 ohm, so we will get 113 milliamp, which is below the peak current of the transistor. In this diagram we have the current through the transistor and the loudspeaker and the power dissipation of the transistor as a function of the collector-emitter voltage. With a decreasing collector-emitter voltage, here we have the collector-emitter voltage. When it decreases, the emitter voltage will increase. And with an increasing emitter voltage, we will have an increasing current through the loudspeaker. So with a decreasing collector-emitter voltage, we will have an increasing current. With the decreasing collector-emitter voltage, the power or the product from collector-emitter voltage and current will increase and get its maximum at 1.25 volt, and then it will decrease again. So we can calculate the maximum power dissipation of 98 milliwatt, and with this we can calculate the temperature increase of the junction, and it is 98 milliwatt times 200 degrees Celsius per watt is 19.6 degrees Celsius. With an ambient temperature of 40 degrees and plus 19.6 degrees Celsius, we are far below the allowed 150 degrees Celsius junction temperature. Here our measurement setup. The blue line is ground or 0 volt, the red line is plus 2.5 volt, the black line is minus 2.5 volt. Here we have a supporting capacitor. Here we have our transistors, the NPN and PNP transistor, and the input signal comes here via these two lines. The black line go to 0 volts, the red line with the signal go here to the base of the two transistors, and here to the yellow probe from the oscilloscope. And the output go here to the purple probe of the oscilloscope, and here with the green line to the loudspeaker and back to 0 volt of the supply voltage. And here we have the signals. The yellow signal is the input signal from the signal generator, and the purple signal is the output signal to the loudspeaker. I increase now the input signal, and we have still below 0.7 volt, and so we have no output signal. I increase it a little bit more, and now we see that at a short time the output transistors are turned on, and we have these plateaus here in between. I make the signal stronger and stronger, and now we can see the output signal is about 0.7 volts smaller than the input signal, and we have these plateaus around the 0 voltage of the input signal. Now a closer look to the spectrum. Here we have 9 kilohertz, and for each division we have 2 kilohertz. So here we have the 1 kilohertz, which is our input signal from the signal generator. Channel 1 is the input signal, and we see that we have a strong signal at 1 kilohertz, and the harmonics are below minus 40 dB. I switch now over to channel 2, which is the output to the loudspeaker, and we see here that we have a strong number of loud harmonics, and this will cause this peeping sound. I switch back to channel 1, low harmonics on the input, and channel 2, strong harmonics on the output. Due to the not satisfying results of the Class B amplifier, we will now build up a Class AB amplifier. Unfortunately, the principal circuit of the Class AB amplifier is not suitable for practical usage. When the transistor gets warmer, the voltage drop of the Base-Emitter diode gets smaller. So this point is not any longer 0 volt, it's a little bit above. The same happens on the negative side with the opposite direction. when this voltage drop gets lower, then it is not zero, it's a little bit below zero. And if we connect two voltage levels, a little bit plus with a little bit minus, with a direct wire, a big current will flow through both transistors. This will warm up the transistors even more, and the voltage drop of the base-emitter diode gets smaller again. So even more current will flow through the transistors, and this go on and on until both transistors disturb themselves. The resistors R2 and R3 are current limiter. Let us assume that these input stage transistors remain cold because they don't carry big currents and have a voltage drop of 0.7 volt here and 0.7 volt here. And these two output transistors carry a lot of current and get warm, and the base-emitter diode drops down to 0.6 volt. So we have here 1.4 volt minus 0.6 volt minus 0.6 volt remain 0.2 volt for these two resistors, and the maximum current which can flow here from the top to the ground is 0.2 volt divided by the sum of R2 and R3. When we now connect the supply line to the collectors of these two transistors, we have not only the wanted 0.7 volt voltage drop on this base-emitter diode, we have also the gain of the transistor and get an additional current gain and a lower input current. Due to the fact that the circuit on the positive supply line is symmetric to the circuit on the negative supply line, and we have here the 0 point, we can do all our calculation only on the positive circuit and transfer our result to the negative side. For further calculation, we will do some assumptions. UR1, this is this voltage, should be not bigger than 0.3 volt. Now we estimate that the temperature increase between the junction temperature of T1 and T2 is not more than 50 degrees Celsius. So we can calculate with the 2 millivolt per degree Celsius a base-emitter diode difference voltage of maximum 0.1 volt. With this 0.1 volt and assumption that our cross current should be not bigger than 50 milliamp, we can calculate R2 and R3 to 2 ohm. We have now two overlaid currents. One is driven by the input signal and drives the current through T2, R2 and the loudspeaker, and the other current is driven by the voltage difference between base-emitter voltage of T1 and base-emitter voltage of T2 and drives the current through T2, R2, R3 and T3. When two or more currents or voltages are overlaid in a linear network, we can use the superposition principle. More about the superposition principle you will find in the video 010EN. There are a lot of calculations, so I will do it with a spreadsheet. Here the important parameters. UB half is 2.5 volt, R2 is 2 ohm, the loudspeaker impedance is 16 ohm, the thermal resistor of the housing is 200 degrees Celsius per watt, the change of the base-emitter voltage with temperature is 2 millivolt per degree Celsius, and here we can set the voltage difference between the base-emitter voltage of T1 and the base-emitter voltage of T2. Here we have the emitter voltage of T2. It's this point. We have here 2.5 volt and the base-emitter voltage drop is 0.7 volt. So the voltage what we can here have maximum is 1.8 volt. So we go from 0 to 1.8 maximum. Due to the fact that we have here also a voltage drop of 0.3 volt, these three lines are very unlikely to reach. Only if we have a transistor with a very high amplification and then a very small current in R1, we will get in this region. This voltage is also our input voltage here. It was our design goal that this voltage is at the same level here. We have here 0.7 volt and here 0.7 volt, and therefore we are here at the same level as on the input. According to superposition principle, we can calculate the current through R2 and the loudspeaker caused by the input signal, and the cross current through R2 caused by the voltage difference of the base-emitter diodes of T1 and T2 separately, and add them later. The input signal driven current is the input voltage divided by R2 and the loudspeaker impedance. The cross current is the delta of the base-emitter voltage divided by R2, and the resulting emitter current is, according superposition principle, the addition of both currents. The collector-emitter voltage is the supply voltage at the collector minus the emitter voltage. The power is the current through the emitter and multiplied with the collector-emitter voltage. The resulting temperature change is the power of the transistor multiplied with the thermal resistance of the housing, and the resulting change of the base-emitter voltage is the change of the temperature multiplied with the 2 millivolt per degree Celsius. We start now with a base-emitter delta voltage of 0 volt, and what we see is that the resulting one is already on the maximum of 0.035 volt. So we go back and go a little bit above this, 0.04 volt. And we see, caused by the cross current, the temperature increases more and even the delta goes higher, and we have 0.045. And now I increase already a little bit to 0.05. And now we see it's now decreasing, so we are a little bit above the stabilizing point, and we can use this data for further evaluation. Now let's have a look on the temperature. We have a little bit above 24 degrees Celsius. Let us assume 25 degree plus the 40 degree ambient temperature is 65 degree. And with 65 degree we are far below the allowed maximum junction temperature of 150 degree. At the power we have 121 milliwatt, allowed are 500 milliwatt, so we are here also okay. And on the continuous current we see we are okay here until there. And here we are a little bit above the continuous current, but far below the 200 milliamp peak current, and this is the maximum of the amplitude, so we have here only small peaks where the transistor is operating on this point. Now we have to calculate R1 and R4. Our assumption was that we have the supply voltage minus 0.3 and minus 0.7 volt, so we have here 1.5 volt, and divided by R2 and the impedance of the loudspeaker, which is 18 ohm, we have 83.3 milliamp. This divided by the amplification of the transistor gives us 555 microamp, and with 505 microamps on 0.3 volt we get 540 ohm, and my next smaller resistor I have available is 470 ohm. Now we calculate the maximum input current. The maximum input current is the maximum current in the emitter divided by the amplification of the transistor. we get the maximum emitter current when the base is on the negative supply line. So we have 5 volt minus 0.7 volt divided by the 470 ohm resistor, and we get 9.15 milliamp in the emitter divided by the amplification, and we get 61 microamp into the base. For the theoretical view and calculation, it was easier to use the plus minus 2.5 volt. For practical usage, it's better to have the input voltage from 0 to 5 volt, and we have then the reference to the negative supply line from the Arduino, and the Arduino will send us 2.5 volt for the silent condition. Also on the output, it's easier to have a single 5 volt supply instead the dual plus minus 2.5 volt supply. To get this, we decouple the DC part of the output signal with a capacitor from the loudspeaker and connect the loudspeaker via the capacitor on one end and the other side of the loudspeaker on the negative supply line. The capacitor is a high-pass filter, and its cutoff frequency must be chosen that it is below the lowest audio frequency. And at the piano, the lowest frequency is 27.5 Hz, so we choose a cutoff frequency of 25 Hz. At the cutoff frequency, the impedance of the capacitor is equal to the resistance of the loudspeaker. So we get for the capacitance 1 divided by 2p cutoff frequency impedance capacitor is 1 divided by 2p 25 Hz 16 ohm. So we get a capacitance of 398 microfarad, and the next bigger capacitor I have available is 470 microfarad. Here our measurement setup. We have a single voltage supply, 0 volt, 5 volt, the supporting capacitor. The 0 volt line goes here to the ground line of the oscilloscope probes, to the loudspeaker, and here to the signal generator. The signal from the signal generator has now an offset of 2.5 volt to be in the middle of the 5 volt supply, and it goes here to the two input transistor bases. We have here the input transistors, the PNP and NPN, and the output transistors, the NPN and PNP. The emitter of the output transistors goes via two 1 ohm resistors to a middle point here and here, and the middle point goes to the capacitor, and from the capacitor we have one line to the loudspeaker and one line to the purple oscilloscope probe. I have used here two single 1 ohm resistors because I have no 2 ohm resistor available. Now let's have a look on the signals. The yellow line shows the input signal from the signal generator, and the purple line the signal at the loudspeaker. I will now increase the signal generator, and we see even with a very small input signal, the output signal is immediately following, and now I increase it more and more. And we see we have not any longer these plateaus here. We have a smooth transition between the top and low side of the sine signal. And we see also that the output signal is smaller than the input signal voltage. And this is caused by the 2 ohm resistors and the capacitor, which build up together with the loudspeaker a voltage divider. I will now go closer to the microphone and increase the voltage further. And now we get on the output signal these plateaus, and the sound did change. And I go back, and we see I can change here the voltage, and we have no change in the sound. But as soon we get the plateau we hear this very high peeping sound, and this is caused by the additional harmonics which are produced when we get these plateaus. And now look on the spectrum. Here we have the 9 kHz signal, the 2 kHz per division. We are now on the channel 1 for the input signal from the signal generator, and we see the 0 dB signal on the 1 kHz, and the harmonics are below -40 dB. And we see a large peak on 0 Hz, and this is 2.5 volt offset that we have added to the input signal to be in the middle of the 5 volt. I switch now over to channel 2 for the output signal, and we see, due to the electrolytic capacitor, the output DC is removed. We have the big signal on 1 kHz, and the harmonics are far below -40 dB. The 1 kHz signal is here also a little bit smaller, as we have seen it in the time signal. And now in the end, an acoustic comparison of the two amplifier classes. That's all for today. If you like my video, give me a thumbs up and subscribe my channel. And to be informed about new videos, activate the bell. See you in the next video. Bye bye.